This is Robert Sapolsky, and you're listening to Father-Offspring Interviews.
Hello, welcome back to Father-Offspring Interviews. Getting started, David from Idaho says, I recently listened to an interview which talked about how, when depressed, the default mode network doesn't get new sensory information to indicate that one need not be stuck in the negative emotions that they're experiencing. Could you elaborate on this, please?
Well, before getting started, I just want to note that if everything works according to schedule, this episode will be posted on Wednesday, March 25th, which is your birthday. Your 3 to the 3rd birthday, and happy birthday, and we love you beyond. Let's see, what was that question? Default mode network. Okay, we've talked about it previously in the context of awe and wonder, in the context of what's happening in your brain when you are bored. In this case, we're talking about it in the really important context of depression. Now, if you want to be super simplifying depression, its symptoms could be broken into 3 main domains. First one, anhedonia, the inability to feel pleasure, the inability to feel anticipation of pleasure, the inability to feel motivated to pursue something that would be rewarding. Second, psychomotor retardation. Everything is exhausting. Just getting out of your bed is the biggest challenge of the day. It is simply all too much. It is exhausting to do. It is exhausting to think. Third, rumination. The negative thoughts just go around in your head again and again and again, and you can't stop them. And for my money, none of those are really pleasing, but I would put rumination up there as one of the most agonizing features of this disease. Your mind will not let you alone. It just keeps running the negativity over and over. So, turns out there's some relevance of this to this default mode network. A little bit of history, functional MRI, brain imaging. It's not where you're looking at the structure of the brain, but you're looking at activity, metabolism in different parts of the brain as you give the subject something to do. And there is always this dogma in the field, which is you got a subject in the brain scanner and you're about to ask them to recite the president's backward or something. And what you see is, as soon as they start, frontal cortical areas activate a whole lot. And as soon as they're done and it's all over with and you can just kick back, there's just this background noise. There's a background burble of brain activity going on when you're doing nothing. And the insight, mostly that of pioneer in this field, Marcus Rakel of Washington University School of Medicine, was to say, wait, the brain is not just sitting there with random noisy burbling. And he began to study what the noise was. And as it turned out, there was a lot of structure to what the brain was doing when you weren't doing anything. And he called this the default mode network. And this turns out to be a really interesting part of the brain in terms of what it does. First off, what comes up with that seemingly random burbling is it's not random. It's the same handful of brain regions that are involved. And most importantly, they show tremendous connectivity and synchrony. When one of them is being in its default state, it is highly synchronized with the other ones. It is not just the absence of something exciting like mentioning the president's backward. Instead, it's doing something when you are seemingly not doing anything else. Now, first off, the brain regions that are involved, and there are some agonizing ones. One of them is the ventral medial prefrontal cortex, which is really interesting. Prefrontal cortex, eggheady cognitive decision-making. Ventral medial prefrontal cortex, that's how your emotions get funneled up into your prefrontal cortex, emotionally influencing the sort of decisions that it makes. What else? Something called the posterior cingulate cortex. Another interesting area, temporal parietal junction. And we'll see in a minute what is interesting about that in the context of the default mode network. Something called the retrospinal pineal cortex, the angular gyrus. There's a whole bunch of these areas that suddenly activate in a synchronized way as soon as you're not doing anything. So what do these areas subsume? Daydreaming, mind wandering, self-reflection, streams of consciousness, rehearsing autobiographical information, just self-referential decision-making. It's the stuff you're doing in your head when you don't have to be doing something else. And amid that, what's interesting there is most of these are about you are daydreaming, you are reviewing your past, you are thinking about your autobiographical details. It is very self-oriented, very ego-oriented, which brings us back to that brain region, the temporal parietal junction. What's it about? That's the brain region where you do theory of mind, where you figure out what somebody else is thinking if it's different from what you're thinking. Whoa, that sounds so externalized. Forget egocentrism of your brain activity. That sounds so looking outward. What it's mostly about is trying to figure out what people are thinking about you. So this whole array of functions, and this coordinated pathway that everybody used to think was just noise. Now, I just went through a whole list of things it's doing: daydreaming and mind wandering and self-reflection and autobiographical. Depending on that particular function, subsets of the default mode network are most active, are most synchronized. Collectively, though, it forms a network. And what that suggests is there's other networks in the brain that wind up being very pertinent to making sense of depression. Now, what we've set up is default mode network is when you are spacing out and daydreaming. Obviously, at the other extreme is this alert decision-making executive function network involving, you bet, prefrontal cortex, in particular, the dorsolateral prefrontal cortex, the orbitofrontal cortex. That's when you're concentrating on making decisions, and it's the opposite end of the world from your default mode network just spacing out there. So we've got one, and we've got the other, default mode, executive function network. So how do you switch between the two? And this is where we bring in the third network of this triple network model, something sitting in between that pays attention to whether this is something you should be paying attention to. If something pertinent, if something salient comes up, it kicks the executive network into action. Pay attention, stop doing the daydreaming back in the default network, focus on this, and as soon as it's over with, this in-between switch flips it back over to activating the default mode network. What is this intermediate part called? The salience network. Figuring out, is this something where you need to be paying attention, or is this a chance to mind wander? What are the brain regions involved in that? Something that's going to become very pertinent: the amygdala, the insular cortex, the anterior cingulate cortex. Okay, so we've got this picture. And what does healthy default mode network function consist of? When you are daydreaming, all the parts are activated and they are disconnected from that uptight executive function network, and they are all highly synchronized. And the second the salience network wakes up and says, aha, something important is happening in the outside world, promptly goes silent and flips over to the other side. Nice, clean transitions, nice, synchronized, coordinated function when the default mode network is in action. Okay, so that's just normal functioning. So what happens during depression? And what is seen is there's a very substantial increase in the activity of the default mode network all the time. A substantial increase in all sorts of parts of it, some of the subparts more so than others, but it becomes much more activated. So this now raises two questions for us. How does this elevated activity of the default mode network get you stuck in rumination, cycles of thoughts that just go around and around and around. And the second question is, why are they negative? Why are they depressive? Why are they aversive? And both have something to do with what happens to that network in between the one switching back and forth, that salience network. As soon as you got depression, what you see is not only elevated activity of the default mode network, but somehow it is able to hooscal the salient network, hijack it into functioning as part of the default mode network. What are the consequences of that? Twofold. Salience network is not functioning anymore to say, hey, let's pay attention to the executive function network. It gets silenced. You just have an echo chamber of thoughts going around and around, extremely resistant to the sort of useful information that might suggest to you that your depressive rumination isn't all that rational. Instead, executive network is dumped out of it. Salience network is hand in hand with the default mode network, and you are just stuck in these loops of rumination. Where does the negativity come from? Go back 30 seconds. What are the regions of the salience network? The amygdala, the insular cortex, the anterior cingulate. These are parts of the brain that generate a lot of negativity. The amygdala, fear, anxiety, aggression, hatred. The insular cortex, moral disgust, gustatory disgust, anterior cingulate, empathic pain. These are kind of downer of brain regions. And during depression, the amygdala is even more interesting. You take a regular old subject and stick them in a brain scanner, and you flash up a series of faces. And what you see is when faces come up that are scary, threatening, or that look scared or threatened, you get activation of the amygdala. Yep, it's about fear and anxiety. You don't see that as readily in people when they are depressed. Instead, what's the amygdala being used for? It doesn't activate its scary faces, it activates its sad faces. It has switched its role. Until you think about it, it hasn't switched at all. Normally, what the amygdala is doing is reacting to the scariest thing out there. The monster, the mugger, the whatever it is that's terrifying you. If you're clinically depressed, what's the most frightening thing in the universe? Anything in the outside world that's going to make you feel sadder. And what we have now is suddenly the amygdala focused on sadness, the insular cortex with its negativity, the anterior cingulate with its empathic negativity, and now they are part of this default mode network, and all they're doing is not only guaranteeing you got these ruminative loops because the salience network isn't paying any attention to the executive network. It's just in here, not only loops now, but dumping all that negativity onto it. That's where the negative rumination seemingly is coming from. Okay, so looking at that, of course, what you want to know is how do you break through that? And it's fairly plausible that some of the leading antidepressants do exactly that. What they do is they weaken the rumination. They strengthen the ability of the prefrontal cortex to ram its way back in there, get the salience network to go back to doing its real job and get things back to functioning. This is also what's happening in cognitive behavioral therapy. Its approach, classically, is focusing on depression as a cognitive disorder, as a disorder of thought, as a disorder of distorted thought, cognitive distortions, where you decide the terrible thing that did actually happen to you back when, your distortion, that's inevitably my present and my future. You overgeneralize it to a pathological extent. And what cognitive behavioral therapy is very good at is trying to deconstruct these cognitive distortions, getting at all this negative affect from a cognitive entry point And what it's often doing is it's trying to give the prefrontal cortex more means to say, you back there in the default, all that ruminative negativity, all that isn't actually fitting reality. It is giving you the tools to counter that overgeneralization by attacking the cognitive distortions in a very, very broad way. So, of course, now let's translate the usual picture. Why are some people, 20% of people, so much more vulnerable to depression than everyone else? Why are a subset of them so vulnerable to rumination as their main symptom? And what we see is all the usual suspects. Genes play a role, early experience, early trauma and loss and adversity play a role. And what do they wind up doing? They're going to influence the sort of salience network you develop. And which direction does it look most? It's going to influence how readily your default network gets caught up in these loops. Everything coming beforehand, the biopsychological stuff that makes perfect sense by now, contributing to why the default mode network and the salience network and the executive function network is more likely in some people than others to dump you into depressive rumination.
All right, well, on a potentially less depressing note, next, Tom from Utah/Yucatan asks, what do we know about, if any, pros or cons of artificial cranial deformation observed in many ancient cultures?
What an unexpected, irresistible question. Artificial cranial deformation, pressing newborns' heads in certain ways continuously so that their skull winds up maturing, growing in a distinctive direction, in a distinctive pattern. Newborn babies, the top of their heads are very squishy because all of the bones up there, they have not fused together yet. There are spaces in between called fontanelles, and there's tissue covering them, but there's openings between the bone plates there. What's that about? Because human babies have this massive challenge, which is fitting through mom's pelvic arch when they're getting born, and having the head being a little bit compressible is advantageous. And the fontanelles slowly disappear over the subsequent year or so. So you look at this and you see a whole lot of cultures took advantage of the fontanelle-ish nature of the skulls of newborns to try to artificially deform them, producing distinctive shapes, as you could see from some of these pictures. What was one of the common things done in a lot of these cultures? You wrap the head and keep it wrapped tightly for like the first 2 years of the kid's life, and what that does is force the skull to grow upward. So that's one possibility. In other cultures, you wrap around here, and what you wind up getting is an indentation. As another form, mom wants to keep you tied to her backpack when she's out carrying you around. And what's done? You spend the first year of your life having this heavy strap around your skull, which winds up producing an indentation as the skull matures. Or then there's other cultures where they went to great efforts to make the top of your head flat. This was what was seen in ancient Egypt. King Tut clearly spent his early years having heavy something or others wrapped around the top of his head and underneath, because when you look at the reconstruction of his head, you can see there's a saddle-shaped depression there where the strip was tied there underneath his chin. And this was all the rage amid the fancy folks at that time. King Tut's parents, Akhenaten and Queen Nefertiti, did this to all of their numerous kids, and this was great. All sorts of other ancient cultures would do this. Heads with artificial cranial deformations of various types found in Iraq from 10,000 years ago, found in ancient Peru, ancient China, found in the Vikings. Okay, so now we know how you go about deforming somebody's skull. If you want to make it point up or have a flat there or flatten out the top or what. And the obvious question is, why did people do this? And basically, I think there were three domains where this would occur. First one, no one intended to do this, but this just helped you do something useful, like keeping your kid tied to the back of your backpack. And this was associated with peasants. And the last known cases of cranial deformation was occurring in Toulouse, France, early in the last century, where people were still binding their kids' foreheads so they could attach them to their knapsacks or whatever they were carrying around. Pure utility, and preferentially among the poor, among the peasantry. The second, why would anyone do this? Royalty, dominant, signs of being the ruling class. And in Egypt, for example, the deformations that flattened King Tut's head went through all the royals. That was the marker of their royalty. All of them have flat types of heads. And what is seen by about 1,000 years later, a little bit of democracy has crept in. Now you're seeing the same deformations in the senior big shot priests as well. So it's beginning to spread outward to some extent. What were people thinking? This somehow made the top of your head more accessible to spiritual reflections on the sky, or who knows what. Now, the third reason is the one that strikes me as most interesting, which is in cultures where it's not just the peasants tying their kids to a pack, and it's not just the rulers, but it's something that everybody in the tribe does. And what this is probably about is a concept we've talked about in the past, a green beard effect. This is this concept in evolutionary theory. What is a green beard? A trait that makes you very conspicuous, and in addition, makes you cooperative with somebody else with the same conspicuous trait. That's how you find like-minded organisms. You can now start reciprocal altruism. And the argument here is this is a green beard effect in the cultures where everybody would adapt this. What's the advantage of a green beard effect? You see somebody from 20 yards away. You have no idea who they are. They're a perfect stranger. But if they happen to be dressed like this, and you happen to be dressed like this as well, you know both of you share certain values. You think the government should educate people and take care of their health for free. You think the government should have very generous parental leaves, that there should be low levels of income inequality, that the military isn't a high priority. Just seeing some, and you know what values you share. And seemingly what was going on there is if you're from the pointy-headed tribe and you see some stranger over there who's pointy-headed, green beard, you know they share a value with you. You know they share the value of, for some reason, liking pointing heads. And you know you would now go out of your way to save that person from a predator, or if they fell on the subway tracks. In those cases, it is probably an identifying mark. And this takes us back a few weeks talking about how circumcision is occurring historically in indigenous populations, occurs at a higher than expected rate among nomadic pastoralists. So you're wandering through other areas and you've got a marker of which group you belong to that way, or a tattoo, or a weirdly shaped head. But now we get to what I thought was the most charming part of the question. What are the pros and cons of head deformation? And try as I might, I could not find anything that suggested some sort of advantage of doing it beyond letting people know your royalty, or keeping your kid from falling off, or recognizing peoples of your tribe. What are the cons side? Here's where I was most surprised. There were no cons. As long as the compression doesn't change the overall volume of the brain case, as far as anybody can tell, this had no effect on function. It might have produced some very hard feelings about your parents from back early in life, but there didn't seem to be any major cons.
All right, finally, Carter from New York asks, if, after the extinction of the dinosaurs, it was the small, early underground mammals who survived, would they have been pair bonding species?
What Carter brings up is something that is impossible to know with certainty, but that we nonetheless have a lot of insights into. So the dinosaurs get wiped out and we start the age of mammals, and it's a pretty pathetic start because there are all these little squirrely tiny mammals running around there. And one plausible thing would be to speculate that this is where pair bonding, monogamy, started. All these little mammals, and there's all these dead dinosaurs around and stinking, and the least you could do to get through each day is to find a beloved. And this would be a picture of the ancestor of all extant mammals on Earth was a monogamous pair bonder. Alternative, they could have been solitary. Alternative, they could have been group living. And the most insights into what the evolution of this was like, and which you started with, was this landmark 2013 paper in Science by Dieter Lucas and Tim Cluttenbrock, two major zoology honchos in the field, University of Cambridge. And what they did was analyze the mating systems of more than 2,500 mammalian species. What they then did was what's called a phylogenetic analysis. How far apart, how related are any two pairs of species? Can you construct an evolutionary tree to figure out where the bifurcations occurred? And traditionally, people would make these phylogenetic trees looking at patterns of bones or patterns of behavior, and the state of art now is to do your phylogenetic analysis, making a relatedness tree out of DNA sequences. So they proceeded to do that, and what did they find? Something really striking. 68% of Earth's mammal species are solitary. Just somebody sitting there alone by themselves, usually a female with the territory, and some nomadic male showing up on the scene. And before you know it, they were heading off to having kids, and the male is gone the next day, and she goes back to being solitary. 68% of Earth's mammalian species are solitary. 23% live in complex multi-male, multi-female groups. What does that leave us? 9% of mammals are pair bonders. That's a tiny percentage. And you now have a lot on your hands to explain how we started at 100% pair bonders, and somehow all these other ones dominated and we're down to only 9%. What this suggests is, from the sheer numbers, the common ancestor was a solitary species. And the most striking thing about 9% of mammals being monogamous pair bonders is that's like an order of magnitude lower than you see in birds. 90% of bird species are monogamous pair bonders, and we know all of that was evolution just conspiring to the point so that two pair-bonded swans could come together and touch their bills and thus make a heart shape for your Valentine's Day card. Birds are pair bonders. Monogamy in mammals is really rare, less than 10%. Okay, so where did that less than 10% come from? We could have one very easy version of it, one very simple evolutionary phylogenetic tree, which would be all of the pair bonders are from the same related groups of species, and they all came from one common ancestor, the one who invented pair bonding, the one who started all off. And in that scenario, you would be able to trace, say, in this diagram, and ignore the species being shown up there, that's just for the colorful trees. You would see, for example, everything in blue are the group living species, descendants of the species that started it. In red, every one of them is a direct descendant of the monogamous species that started it. And in brown, the mammals who say, oh, I think we're in an exclusive relationship, but we haven't actually talked about it because that would freak him out. But I'm getting hints that maybe he's not being all that committed to it, which is kind of freaking me out. Those type of mammalian species. That would be the simple picture, which is everybody of a particular social system are the descendants from one single ancestor. That's not what they saw in this study. And instead, something much more interesting, which is monogamy kept occurring spontaneously, independently, all across the animal order there, 61 separate independent times in which phylogenetic trees suddenly had a species in there that was pair bonding, which gave rise to pair bonders, which gave rise 61 separate events they were able to show. And you can see a version of it here, which is, you see the pair bonders are very rare. And most importantly in this diagram, they don't have a shared ancestor, one that only they share and are not shared along with solitary or group living species. And you see most of the monogamous mammals are primates or carnivores, but even there you see this spontaneous starting of monogamy at various points in the tree. For example, looking here, we look at the apes, and who are the pair bonders? Us and gibbons, those wonderfully singing gibbons, lesser apes, and they are far from us. In between us and gibbons are gorillas and chimps and orangs, so that we and the gibbons did not share a common monogamous ancestor. It was two separate events that started this off. Okay, so this brings us now to the obvious question: what was the driving force evolutionarily for this small subset of mammals evolving monogamy? And just to follow our pattern here, this is explained, or at least three models in three different domains on the plane in Spain. The first one is obviously pair bond when the males are willing to put in parental effort. That's exactly when you want to get a stable pair that will stick with each other through multiple seasons of mating. If you have biparentalism, that seems fairly plausible. When you look, though, at the pair-bonded species, they don't have statistically higher rates of biparentalism among them than you see in other species. That's not only about half of the pair bonders show any sort of male paternal behavior. So that doesn't explain much. Second possible model, infanticide. Now, we've talked about this, that a competitive strategy for a male of some species is he's an outsider and he's now managed to boot out the guy who has his whole harem of females, who's been mating with them and passing on copies of his genes. And if the new guy is not going to be around for long, and most of these females are pregnant or nursing, he's going to be out of there before he even has a chance to increase number of copies of his genes. What's the horrible logic there? Kill the infants. Kill the infants because the females will stop nursing, cause the females to miscarry through harassment. In either scenario, she soon will be ovulating again, and you can pass on copies of your genes. And we saw that there's subsets of species in which competitive infanticide like this occurs. It's totally interesting. So second obvious explanation for monogamy, it's to prevent infanticide. It's to get stable pairings so that you always have at least some of a safety net against some infanticidal male showing up. You look at the 2,500 mammalian species, and there's no particular support for that. What you find instead, most plausibly, and this is what the pair argued in their science paper, is a socio-ecological model. If you're a female, food is very important to you. On some fundamental level, it's more important to you than it is to a male, because just going through reproductive cycles are really expensive. You thicken uterine walls and you build that, and then you slough them up. And pregnancy, my God, pregnancy and nursing, they're so calorically expensive. While all males need to come up with a couple of sperm and they're in business, females are very constrained by food availability. And what you get in ecosystems where resources are patchy, here's something good, there's something good, rather than like a continuous rainforest in places with patchy resources, females establish their territories around these resources. A clump of fruiting trees, things of that sort, ones that are a whole lot more localized in their nutritional value than just charging across a whole plain, eating every fourth blade of grass. In subsets of species that have areas that have patchy resources, females tend to form solitary territories around their resources. If these territories are far enough apart, the male who wants to show up there and pass on his genes, he does not possibly have a hope for the energy of being able to dominate 2 of these territories, let alone 3 or 100. He's kind of forced by default into picking one and staying there monogamously. And across all these different species, you get patchier resources, the most patchy resources in pair bonding species, followed by solitary species, followed by group living species, which are most likely to have 1 billion foods available. You are more likely to find very singular food resources like fruiting trees in pair bonding species. Most fruit eaters are pair bonders. Hardly any among the solitary, like basically none at all, where that's a big part of their diet. This pattern, the females disperse to make sure they can get enough food in these patchy ecosystems, and the males have to settle down with one female, and that's all they can manage. And before you know it, you got silver wedding anniversaries, and that's probably where it evolved from. One final point that was implicit in the question. The question asked about social monogamy. And that's a different thing from what people are now calling genetic monogamy. Social monogamy, you've got this pair bond and they stick together through thick and thin and they forage together, and with any luck the male helps out with childcare on the 2 of them, and they are socially monogamous. But here's where the heartbreak comes in, and this was originally discovered with prairie voles, who were the textbook case of monogamous voles in contrast to their polygamous cousins, mountain voles. Prairie voles, they had wonderful American prairie values. They were monogamous, and it turned out they were socially monogamous. They maintained a pair bond, but both of them at times would sneak off and have opportunistic matings with someone else. Thus, we have a contrast in a lot of these species. Social monogamy is not the exact equivalent of genetic monogamy. There's a lot of wiggle room between the 2. Nonetheless, this was a study of social monogamy across all these mammalian species.
And that's episode 104. I'm Offspring Sapolsky, and thanks for your continued support of Science and the Beard.